Welcome everyone. In today's lesson, we are going to learn one of the most important ideas in statistics, hypothesis testing. Many students feel that hypothesis testing is difficult because it includes many terms such as null hypothesis, alternative hypothesis, alpha level, critical region, z-score, type 1 error, and type 2 error. But actually, the main idea is simple. Hypothesis testing is a formal method for answering this question. When we observe a result from a sample, is that result strong enough to believe that something real is happening in the population? For example, suppose we teach students using a new method. After the lesson, their exam score increases. But we must ask, did the teaching method really improve performance or did the score increase just by chance? That is exactly the purpose of hypothesis testing. So, in this lesson, we will not only memorize formulas, we will understand the logic behind the formulas. We will see hypothesis testing as a decision making process under uncertainty. By the end of this lecture, you should understand how a researcher moves from a question to a hypothesis to data collection to calculation and finally to a statistical decision. This slide shows the basic logic of hypothesis testing. In statistics, we usually want to understand a population. A population means the whole group we are interested in. For example, all students in a university, all patients in a hospital, or all athletes in a team. But in real research, it is often impossible to measure everyone in the population. So instead, we take a sample. A sample is a smaller group selected from the population. Now, the important question is this: can we use the sample result to make a reasonable conclusion about the population? Hypothesis testing follows a clear process. First, we state a hypothesis about a population parameter. A parameter may be the population mean, such as the average exam score. Second, based on that hypothesis, we predict what kind of sample result we should expect. Third, we collect actual data from a sample. Fourth, we compare the observed sample result with the prediction. If the sample result is very different from what we expected, then we may say the hypothesis is probably not correct. But if the sample result is close to what we expected, then we do not have enough evidence to reject the hypothesis. So, hypothesis testing is basically a comparison between what we expected and what we observed. In hypothesis testing, we always begin with two competing claims. The first one is called the null hypothesis, written as H0 or H0. The null hypothesis usually says that there is no change, no difference, or no relationship. The second one is called the alternative hypothesis, written as H1. The alternative hypothesis says that there is a change, a difference, or a relationship. Let us use the simple dog example from the slide. The null hypothesis says all dogs have four legs. There is no difference in the number of legs dogs have. The alternative hypothesis says some dogs may have a different number of legs. For example, 20% of dogs have only three legs. This is only a simple example, but it helps us understand the logic. In real research, the null hypothesis often represents the existing belief, the normal condition, or the status quo. The alternative hypothesis represents the researcher's expectation or the possible effect. For example, in an education study, H0, the new teaching method, does not change student scores. H1, the new teaching method, changes student scores. Notice that hypothesis testing does not begin by trying to prove the alternative hypothesis directly. Instead, it begins by assuming that the null hypothesis is true. Then we ask whether the data are unusual enough to reject that assumption. This is very important. We do not prove H1 directly. We test whether H0 becomes difficult to believe. Title: The Four-Step Engine of Statistical Testing. Approx duration 1 minute 30 seconds. This slide gives us the four-step engine of hypothesis testing. Step 1: state the hypothesis. Here we write the null hypothesis and the alternative hypothesis clearly. Step 2: set criteria for decision. Before collecting or interpreting the result, we decide how much evidence is required to reject the null hypothesis. This is where the significance level or alpha level becomes important. Step 3: collect data and compute. We collect sample data and calculate a test statistic, such as a z-score or t-score. Step 4: make a decision. Finally, we compare our calculated value with the decision criteria and decide whether to reject or fail to reject the null hypothesis. The case study shown here is about the effect of alcohol on memory during cram sessions. The dependent variable is the exam score or memory performance. The independent variable is the intervention, which may be an alcohol pamphlet or treatment condition. The baseline population value is shown as 85 based on previous semesters. So the research question is, Thus, the intervention group's mean exam score differ from the known population mean of 85. This example will help us understand the full hypothesis testing process from beginning to end. Now let us focus on step 1, stating the hypothesis. In this example, the population mean is 85. This means that historically or based on previous data, the average exam score is 85. The null hypothesis says the intervention group's mean exam score will not differ from the population. In symbolic form, we can write H0 m equals 85. Here, m represents the sample mean or the mean score of the intervention group. The alternative hypothesis says the intervention group's mean exam score will differ from the population. In symbolic form, H1 m is not equal to 85. This is called a non-directional or two-tailed test. Why? Because we are not saying the score will definitely increase or definitely decrease. We are only saying it will be different. The difference can be in either direction. The sample mean may be higher than 85 or it may be lower than 85. That is why both tails of the distribution are important. In a two-tailed test, we are looking for an unusually high result or an unusually low result. So the first step is complete. We have created two competing realities. One says no difference, the other says there is a difference. Now we move to step 2, setting the criteria for decision. This slide shows the normal distribution. The middle area represents values that are likely to occur if the null hypothesis is true. The red areas on both sides are called the critical regions. If our calculated test statistic falls into one of these red regions, we reject the null hypothesis. The alpha level, written as alpha, represents the probability of rejecting the null hypothesis when it is actually true. In simple words, alpha is the risk level we are willing to accept. Common alpha levels are 0.05, 0.01, and 0.001. In this case, alpha is 0.05 because this is a two-tailed test. The 0.05 is divided into two sides. So each tail contains 0.025 or 2.5%. For a two-tailed test with alpha equal to 0.05, the critical z values are usually z equals minus 1.96 and z equals plus 1.96. This means that if our calculated z-score is less than minus 1.96 or greater than plus 1.96, the result is considered statistically significant. But if the calculated z-score is between minus 1.96 and plus 1.96, then the result is not unusual enough to reject the null hypothesis. So, before looking at the final data, we draw a clear decision boundary. This is important because statistics should not be based on personal feeling. It should be based on a predefined rule. Now we come to the calculation step. The slide shows the formula for the z-score. Z equals m minus mu divided by 7m. Let us understand this slowly. The numerator, m minus mu, is the signal. M is the observed sample mean, mu is the population mean. So m minus mu tells us how far the sample mean is from the population mean. In this example, the sample mean is 90 and the population mean is 85. So the signal is 90 minus 85 equals 5. This means the sample mean is 5 points higher than the population mean. Now look at the denominator. The denominator is 7m, which represents the standard error. Standard error tells us how much sample means are expected to vary naturally because of random sampling. In the slide, the population standard deviation is 8 and the sample size is 9. The formula for standard error is 7m equals sigma divided by the square root of n. So 7m equals 8 divided by square root of 9. Square root of 9 is 3. Therefore, 8 divided by 3 equals 2.67. Now we calculate the z-score. Z equal 90 minus 85 divided by 2.67. That becomes 5 divided by 2.67. So z equals 1.87. What does this mean? It means the sample mean is 1.87 standard errors above the population mean. Now the question is 1.87 large enough to reject the null hypothesis? To answer that, we move to the decision step. This slide shows the final decision. We already set our critical values as minus 1.96 and plus 1.96. Our calculated z-score is plus 1.87. Now compare the calculated z-score with the critical value. The z-score of 1.87 is close to 1.96, but it does not pass 1.96. Therefore, the result does not fall inside the critical region. Because it does not fall inside the critical region, we do not reject the null hypothesis. The correct statistical wording is we fail to reject H0. We do not say we accept H0. This is an important point. Why? because failing to reject the null hypothesis does not prove that the null hypothesis is true. It only means that the current data are not strong enough to reject it. So, in this example, the conclusion is the intervention did not show a statistically significant difference from the population mean of 85, even though the sample mean was 90. The difference was not large enough compared with the expected sampling variability. This teaches us one important lesson. A visible difference is not always a statistically significant difference. This slide helps us understand z scores intuitively. A large z score means the sample result is far away from what we expected under the null hypothesis. If the z score is very large, either in the positive or negative direction, then the result is unlikely to have occurred by chance. In that case, we may attribute the difference to the independent variable or treatment effect. For example, if a new teaching method produces a very large z score, we may suspect that the teaching method had a real effect. On the other hand, a small z score means the observed result is close to what we expected under the null hypothesis. In that case, the result may be explained by random sampling error. So the basic interpretation is large z score less likely due to chance, small z score more likely due to chance. But remember, large or small is not based on personal judgment. It depends on the critical value and alpha level we set before the test. In our example, the z score was 1.87. It was somewhat large but not large enough to pass that critical value of 1.96. Now we discuss errors in hypothesis testing. This slide shows a matrix with two dimensions. One dimension is the researcher's decision, reject H0 or retain H0. The other dimension is actual reality. Either H0 is actually true or H0 is actually false. Sometimes our decision is correct, but sometimes we make an error. A type 1 error happens when we reject H0 even though H0 is actually true. This is also called a false positive. In simple words, we say there is an effect, but in reality, there is no effect. For example, we conclude that a new teaching method improves scores, but actually it does not. The observed result happened only by chance. A type 2 error happens when we fail to reject H0 even though H0 is actually false. This is also called a false negative. In simple words, there is a real effect, but the researcher fails to detect it. For example, the teaching method really improves scores, but our study does not find enough evidence. So, hypothesis testing is not a perfect truth machine. It is a structured decision system that always includes some risk of error. This slide shows that type 1 error and type 2 error are connected. Type 1 error risk is represented by alpha. Alpha. This is the probability of false positive. Type 2 error risk is represented by beta. Beta. This is the probability of false negative. When we lower alpha, we make it harder to reject the null hypothesis. For example, if we use alpha equal to 0.01 instead of 0.05, we require stronger evidence before rejecting H0. This reduces the chance of type 1 error. But there is a trade off. When it becomes harder to reject H0, we may increase the chance of missing a real effect. That means type 2 error can increase, so we cannot simply minimize one type of error without affecting the other. In research, the choice of alpha depends on the context. If a false positive is very dangerous, we use a smaller alpha. For example, in medical drug testing, we do not want to claim that a treatment works when it actually does not. But if missing a real effect is very dangerous, then we also need to think carefully about type 2 error and statistical power. This is why hypothesis testing requires balance. This slide explains what affects the z score. Remember the z score formula. Z equals the difference between the sample mean and population mean divided by the standard error. So there are three important levers. First, the magnitude of difference. If the difference between m and mu becomes larger, the numerator becomes larger. That makes the z score larger. Second, the sample size, n. When sample size increases, the standard error decreases because standard error is calculated by dividing the standard deviation by the square root of n. So a larger sample size gives a smaller standard error, and this can produce a larger z score. This is why larger samples often give more precise estimates. Third, the variability of scores sigma. If the data are highly variable, the standard error becomes larger. That makes the denominator larger, and the z score becomes smaller. In simple words, a larger difference increases the chance of significance. A larger sample size increases precision. Greater variability makes it harder to detect an effect. This is very important in research design. Before collecting data, researchers should think about sample size, expected effect size, and variability. This slide shows the assumptions behind a valid hypothesis test. A hypothesis test is only meaningful if certain conditions are reasonably satisfied. The first condition is random sampling. The sample should represent the population. If the sample is biased, the conclusion may also be biased. The second condition is independent observations. Each data point should be independent from the others. For example, one student's score should not directly determine another student's score. The third condition is constant variability. The variability should remain reasonably stable. If variability changes dramatically across groups or conditions, some statistical tests may not be appropriate. The fourth condition is normal distribution. For many hypothesis tests, especially z tests and t tests, we assume that the sampling distribution is approximately normal. This allows us to calculate probabilities using the normal curve. In real research, these assumptions are very important. If we ignore assumptions, the test result may look mathematically correct, but the conclusion may be unreliable. So, before applying a hypothesis test, we should always ask, was the sample selected properly? Are the observations independent? Is the variability reasonable? Is the normality assumption acceptable? Good statistics begins before calculation. It begins with good research design. This final slide summarizes the whole lesson. Hypothesis testing can be understood in four phases. Phase 1, anchor. We define the status quo, which is the null hypothesis, and the anomaly, which is the alternative hypothesis. Phase 2, gatekeep. We set the significance level, alpha. This controls how much evidence is required before we reject the null hypothesis. Phase 3, isolate. We calculate the signal to noise ratio. In this lesson, that ratio was the z score. The signal was the difference between the sample mean and the population mean. The noise was the standard error or the expected random variability. Phase 4, judge. We compare the calculated z score with the critical value. If the calculated value enters the critical region, we reject H0. If it does not enter the critical region, we fail to reject H0. The most important message from this lesson is this: hypothesis testing is not about proving absolute truth. It is a formal system for making decisions under uncertainty. It tells us how much evidence is needed before we change our belief from no effect to there is probably an effect. In our example, the sample mean was 90 and the population mean was 85. The z score was 1.87. But because 1.87 did not reach the critical value of 1.96, we failed to reject the null hypothesis. So the result was not statistically significant. This does not mean there is definitely no effect. It only means that the evidence was not strong enough under our selected alpha level. That is the heart of hypothesis testing. Make a claim, set a rule, calculate evidence, and make a disciplined decision.